but
Okay.
that's how we have tried to. So, good morning, Professor Gokan Sharma. We welcome you for the day two.
Good morning, everyone. Today I'll be
Yes.
in the background, so
Yeah, sure.
Dr. Das will take charge
Yeah,
today.
yes, sir. Yes, sir.
Tomorrow, starting tomorrow, I will
Yeah,
continue
yeah. Thank you,
with the.
thank you.
All right.
Oh,
Thank
yeah.
you.
So, good evening to students. Good morning to both the professors. We thank you for accepting our invitation for this collaborative teaching on process architecture. So, this is our day two. So, we have with us Professor Adya Kusum Das from University of Wisconsin, Platteville, and Dr. Gokarn Sharma, who is from Kent State University, Ohio, USA. So our today's proceeding is Dr. Das will be continuing, and today's topic is on fork join framework, divide and conquer, analyzing the parallel programs and Amdahl's law. So yesterday also he talked and given us a very good examples, a program of Java. He has already provided us the soft copy of the code. So today he will be moving further for analyzing the fork join framework. And Dr. Das, the floor is yours now.
Hi. Hello, good morning, everybody, and good evening, India. So, well, I am really delighted to have today's session. And first of all, once again, congratulations, Dr. Gajjar, for getting the opportunity to work with FPGA on the Xilinx board. And congratulations for as your project has been accepted at an international level. I wish you all the success, and I wish you all the success to the Nirma University. So, all right. Anyway, so let us start today's session. But before going to today's lecture, any question from yesterday? Anyone, any of the participant, any of the students? All right, if there is not many questions, then let us go for today's session. And today we are going to see more example of a parallel program and fork join using the fork join framework. And so let's start today. So let me share my screen. And so, all right, I hope you all can see my screen now. Yeah. So,
Yes.
sure, thanks. So, what we have done yesterday, so let me just have a quick recap of what we have done yesterday. So, we have started with I mean, we have started with the introduction where we have discussed about different better and faster computation. I have told you how the computer can be better, hardware can be faster and cost effective. And there we have discussed about different laws like Pollack's rule, Amdahl's law, Gustafson's law, Dennard scaling, Moore's law, all these different laws. I have also showed you the technology roadmap and where we are, I mean, in this course, where we are actually working. And then we have divided the course, and also I have started with the fork join based parallelism, where I have shown you simple basic Java program to discuss all these things. I mean, discuss like sequential versus parallel program. So we have discussed like how a parallel program can offer speed up, but how it imposes challenges also. And we have discussed about some brief history and discussed about the parallelism versus concurrency. What are these? Although they are related concepts, but there are subtle differences. We talked about that. And then we have started our Java code understanding. And then also we have discussed our Java programming using the model called shared memory explicit threads, which what type of things that we have discussed yesterday. And also like the other, we also discussed like the other parallelism and concurrency model, although we did not see any code example in here, but those are, and maybe those should be the topic for any other future topic, future course. So and then here I have started all these Java related examples, like how to exploit the parallelism in your code. Now also what I have shown you, how to create the thread subclass, and then here we have shown like step by step, I have shown you like how you can implement a Java code. And also at the same time, I have shared all the code with Dr. Gajjar. Possibly you have received the code, or you will receive the code implementation by the end of this lecture. And those codes will help you in tomorrow, after tomorrow, when Dr. Sharma will discuss the project. Possibly you can make use of those code to implement your project. So that that's what we have done. And well, anyway, here we have discussed about like thread.start method, and then we have discussed about the join method, means how to wait for the thread to make the result accurate, to remove any chance of anomaly. So we have discussed about thread start, thread join, and then how to add all the answers to get the sum. So, well, this sum, we have taken the example of sum for the entire lecture, because sum is very easy to understand. Well, I mean, I'm sure that sum is not something, not a very good example that really needs parallelism in the real world. But well, it's very easy to understand, because all of us are, we know that how to add for a few numbers. So it's very easy to understand, and that's why we have picked this example. And then you can easily change the code that I have supplied. You can easily change the sum function to something else, let's say some complicated function, and you can do your own work. All right. So today what we will do is we will basically discuss about the code that we have written, and then we will start analyzing the code. Possibly all those things we will do today. So so the code that I have shown yesterday, that code was actually poorly written, as I have told. The code has several hard-coded part. The first thing that we have shown, like there were several hard-coded part. Like as you can see, the number of processor over here, it is written as 4. So of course you have to parameterize all these things in order to get the actual, to make utilizing all the processor using inside a machine. So well, why parameterize is necessary? Well, if you are trying to use a machine, try to run the same code in a machine where the number of processors are less than the previous machine, then it's okay. Because as we have told, one of the strategy to write good parallel program is increase the number of threads. I mean, the number of threads should be many more than the number of processor, so that everything is load balanced. So but whenever you will go from one machine to another machine where the number of processors are really bigger, then if you do not parameterize it, it cannot take the advantage of those many processors, right? So that's why the parameterizing is so important. And also I have shown you the code how you can utilize those parameterizing method using this Java fork join library in the fork join introduction Java program. So you can feel free to use those functions from my code, and you will be able to write a nice parallel program. So, and not only that, also I have discussed like how not only all the threads, but you need to know like how many processors are available now at this point. So those things are also very much important to write, and so like that. And so also we have told like what is a load imbalance. Means let's say when sorry, so load imbalance means, let's say you have to divide the data, the fair share of the data to each of the threads, otherwise there will be a big problem. So this is one of the example that we have discussed, I believe, in the last lecture, that how to deal with the load imbalancing problem. Just add as many thread as possible. Well, of course, I mean, that will basically this load imbalancing problem will disappear, because the processor pool will get, I mean, thread pool and processor pool will get lots of different threads to assign for multiple core. So this load imbalance problem will be gone anyway. And so that's one of the strategy. However, it's not that easy. Like for example, so what happens is now if you just naively increase the number of threads in your code, then the thread creating overhead will be significantly more. What does that mean? So technically, let's say let's understand it technically. So what happens here, let's say we create only n equals 1 thread to process n element, or process every n element. So there is only n number of threads. So now let's say this it should be array.length anyway, so this should not be n, I'm sorry. So here combining the result, so now what we are doing is basically if we increase n, that becomes linear in the size of array. So previously what we have written, only there are 4 pieces of threads, and that we needed to combine. But in the extreme, what can happen, let's say you have 100 elements, and let's say you have like 100 elements and you are creating like 100 different threads or like that. Then you are assigning only one element in one thread. So you are basically not taking any advantage of the sum in the other extreme. So you have to balance between those two. So your thread should be somewhere in between, so that it does not grow linearly. That's the main idea. It should be properly optimized to take the advantage of the multi-core system, because otherwise the overhead will be significantly more. So basically if you just grow linearly, what will happen, sum is a very inexpensive operation. It is just doing addition. All right, so that may take like, let's say just a fraction, a few nanoseconds maybe. But whereas the thread creation process itself will take milliseconds of time, which is significantly more, 1,000 times more than nanoseconds. So what will happen, eventually you will end up in a degraded performance if you just naively increase the number of threads. All right, so that type of problem will be there, and you have to look for that. So a much better idea is always dividing and conquer process. So from here actually what it is, basically you will divide the entire array into several multiple short problems, and then using a recursive action class you can easily implement the small part of the program, and then you just join the result following the divide and conquer strategy. So what happens, so it is very straightforward implementation. I'm going to show you using the recursive action class or recursive task class. So whatever, and then you can use the parallelism for this recursive call. So all of you who has the idea of a little bit program, you all know what is a recursive task, right? I mean, it is just creating the similar function again and again and again. So what happened, every function calls are basically responsive, are basically given to one of the thread. So the number of threads are being calculated automatically by this divide and conquer strategy whenever you are writing, I mean, how you want to divide and conquer. You really may not need to like a hard code all these things, but it can be taken care of automatically, or even if you think of like doing coming up with the optimal number of threads, you can easily check like how many divide and conquer processes are happening, and then you can just write your code. So divide and conquer is the strategy to come up to do the better addition algorithm, better algorithm for sum. And it's not only for sum. Sum is a very small operation, but it works for a significantly many more problems. So those things you can try in your program. So let's basically what we are going to do, we are basically going to run this sum thread function using this type of recursive algorithm. So as you can see, sum thread left is joining, like it is creating another sum thread function, calling the another object and creating the function, like it is having the array, means it is making 1/2 of the array, and this is taking care of the another half of the array and summing it. So this way it is just chopping off the array again and again and again until some base condition reach, and then it basically use this start and join method to do the summation. So basically, instead of saying that 2 elements or 3 elements or 4 elements one at a time, you are doing a different approach. You are halving the array every time you are halving the array. Then focus on the left and right side, and then again half the left side, half the right side. Then you got 4 different parts. Then again you just do another half of the array, and in that way you are basically proceeding. And once you get the result for everything, then you just merge all the different steps. Okay, so that's a much better approach. So let us see how to so let us see how to write the code for all these divide and conquer and everything. So let's say these let me see which part of the code actually. Yeah, so here it is a recursive addition that I have shown. So this is the actual Java code, which is basically the integer. So here there is a class where we have created a class called sum array, and which is actually extending to recursive task. And then first we have decided to divided it into, I mean, we have initialized some of the variables indicating the array first index, the end index, and the entire array. And we have just used a constructor, just stored those variables. Okay, so here the constructor declaration is very important, because you are going to having the array every time. So here actually basically what you are doing, so here if a high minus low means it is a sequential cutoff. So sequential cutoff, I have just initialized it to some number over here. It can be anything basically. It can be 1, 2, 3 or 100, something like that. I was just experimenting with different numbers, so that how can we optimize all these things. So now what is happening, whenever the number is high minus low, after once you started chopping off the array into half, and then again half, then again half, then again half, whenever the amount of element in one of the segment or in one of the partition is less than the sequential cutoff, that like this 100 over here, then it will do the addition just in a normal way. It will start from the beginning index of the array, that is low, and it will go until the end index of that partition of the array, that is high, and then it is just adding the elements. That's it. That's what it is doing. It's the basic addition. Otherwise, if it is not greater, I mean, if it is greater than sequential cutoff, like there are more than 100 elements, let's say 200 or 300 elements in a partition, it will keep on chopping off the array using this call. So this is basically calling this new sum array, which is basically calling this constructor with the new array that you have. So with this array, and the indexes, the low index have been changed. So you are basically, it is the lower part of the, I mean, left hand side of partition of the array, and then again another call you are making the similar call, but this time you are basically making it like high plus low to 2, that is the right side part of the array, the higher part of the array, high plus low divided by 2 to high. All right, so these things you need to do, and then what you can do, it's like after that you can just do the left forking and joining and all the different things you can start doing. So that's how you can do the divide and conquer. The main thing is happening over here. Instead of using, like, let's say 4 or 5 like different types of threads, basically you are letting the program, I mean letting your algorithm decide what can be an optimal number of threads. All right, so that's the beauty of divide and conquer. If you can implement the algorithm properly, it really works. So this is one example of divide and conquer. And well, so after that, everything is pretty similar. Now there is a class called demo3 where I have created a fork join pool over here, just like this. And from here, there is another sum wrapper class, which is basically calling the fork join pool dot invoke using this new sum array, and then passing the entire array to this class over here, in here where the divide and conquer addition is taking place. And from the main function, I have just called these I have just simply called these sum function over here. So let me just take this part of the code out from here so that you can easily understand, and let me paste it here. So as you can see, so sum is the wrapper class, and from here we are basically calling this sum function. Makes sense? And now if I just run it, you will see that well, okay, it is taking some time because my MacBook is really low in number of processors and everything, so it takes time sometime. So here it is basically giving you all the different results and everything. So that's how you can implement all the different results. All right, so here it is an example. So that's it. And so now let me ask you any question. So I mean, if you have any question, please let me know. So is it clear how to implement this divide and conquer algorithm?
Yeah, so Professor, I have already shared the code yesterday night itself with the students, and we'll see that how they implement it in Java, because some of them need to understand the Java. So you have shared your institute link, so they will do the practice on that. Yeah, please go ahead.
Sure. Thank you. So yeah, if you have already understood how to implement the logic of divide and conquer, so that's how you can start writing the the multi-threaded program for multi-core computation, and you will be good. So as I was saying, that it really works if you go for the divide and conquer. So with enough number of processors, here the total time of the time. So here is some of the asymptotic analysis of the entire algorithm. With enough number of processors, the total time is the tree height actually, which is basically order of log n, assuming there are total n number of data elements, and you are just using divide and conquer. So if there are n number of elements over here, so the total height of the tree from the top level to bottom level over here, it will be order of log n every level. So this is level 1, level 2, level 3, level 4, level 5. So there is only 5 level, whereas there are 2 raised to the power 5, so exponentially more number of elements in the array. So that's what it is happening. So order of log n is the height. So this is optimal and exponentially faster, of course faster than the sequential run. Order of n is of course greater than log n. So it works much better. So but what happens, but the reality is that we usually have p less than order of n processor, but we are not really sure whether it is order of log n processors or not. So when you are doing divide and conquer, make sure that you have a lot of elements, and at the same point of time when you are doing like using a lot of elements, make sure that everything is you have an appreciable amount of memory where everything can be stored. So basically what you can see here, if your data size is more, if your data can be placed in the memory properly, then using this divide and conquer, you can get significantly better advantage. Well, and that's why I was saying, that's one of the thing. And that's what one of the thing you need to remember. You cannot just expect that you have like 100 elements and you are just adding 2 numbers and you are going to get advantage from the parallel program. No, it may not happen. Thread creation time may dominate always. So for example, so here actually what happening, so let me go to the code, and now let me just focus on the time here. Let's say over here, sorry. So let me just comment out the result lines, and let me just run this program. So here, let me show you what may happen in your laptop, but do not lose what is happening. Okay, so it is just taking some time. So here what you can see most of the time in your machine, that 400 per sequential runtime is less than parallel runtime. Okay, so why I am saying that, you may come across this issue, but that does not mean that multi-core computing is not showing its benefit. It only means that, well, this laptop or this home machine is not very good to handle multi-core processes, because our machines are very limited in number of processes, though they have like different types of number of threads, thread handling capability. Also it has some memory issues, like my machine has only 4 gigabytes or 8 gigabytes of memory, which may not be a great choice for multi-core computing. On top of that, SUM is a very easy example where instead of just adding 2 numbers, you are creating threads. So that here also the thread creation times dominate. So you always have to remember that, well, this is the process, divide and conquer. Maybe the sum is not a great example. Maybe your laptop is not a great computer to show the multi-core computing, but whenever you will get access to some, let's say, server type of computer, and a big chunk of problem, like with a 1 terabytes of data, or or at least several hundred gigabytes of data, with more amount of, like, let's say 256 gigabytes of memory, let's say 16 different, I mean, let's say 32 different cores or something like that. At that point of time, it will start showing its actual benefit. At that time, what you need to do, all your code will remain same over here, just you need to change the logic for this sum. So that way you can be a great, that way you can start practicing the multi-core program. So that's what we are trying to teach you, that, well, you got the structure or the skeleton code, and then based on your requirement, you can easily change it. Okay, so let's go back to the PowerPoint now. Well, so those are different types of theories, and I have shared the code for your initial understanding. Now, what happens? So now, when we are trying to write some realistic program in multi-core, we have to think of several things. I mean, everything does not go as the theory is mentioning. Well, of course, theory is to standardize all the different things, but sometimes when it comes to the practical or systems use cases, you may need to tweak several things a little bit, and you need to know a little bit of better understanding of the system. So for example, like, use a sequential cutoff, like 500 to 1000 in a bigger server kind of machine. We have seen, like, it works, it can give you better efficiency. If you go like more than 1000 threads, or if you go for like more than 1000 sequential cutoff, the performance starts degrading because of the thread creation overhead, memory issues, L1 and L2 level caching, all the different things come into picture, and you do not get the promised the level of parallelism, level of efficiency. So, and also there is like eliminates all the recursive threads creation, because it eliminates the bottom level of the tree. So those things you basically need to take care of. Now, well, so the bottom line is, when it comes to the real coding, you need to remember some of these issues, and you have to take care of all those different issues. So what you need to do in parallel programming, do not be very much wasteful about creating threads. Always remember, your thread creation process has a significant overhead. So be very cautious when creating the threads, all right? And that can make your program immensely faster. I will show you an example. Anyway, so so what you need to do, when creating a thread, you are already in another thread. That's what you have to remember. Well, let's say you have so in divide and conquer, let's say this is one thread, you are creating two different thread over here. Now let's say this process is done, and do not just stop the thread and then create another thread. Try to make use of these thread once again. All right, so these things you need to do, how to reuse all the threads, so that unless it is not really necessary, it will not create an extra thread and add some extra overhead in the memory. So those things you need to remember. So what you have to do is one of the very nice strategy that Java fork join program library offers. It is like using this start method and this run method. So what happens is the main difference between, so one of this code in the left hand side code, let's say your some program is implemented, and after that you have written like left dot start, right dot start, left dot join, and right dot join, means you are starting both the threads, and then it is waiting in this join line, it is waiting for the left hand side part of the array to complete, and right dot join means this thread is waiting for the right hand side part to end. All right, so all these things, and then you are just adding these two numbers, left dot answer and right dot answer. So from this left side and right side summation. Now here also all the summation logic are all similar, no problem in here. But what you can, if you notice minutely these two code, you will see a different construct. Here we have used left dot start and then right dot start, but here what we are doing, left dot start and then right dot run. So what is the difference? Difference you can see in the bottom note of the slide. Main difference is that the left code snippet is using start and the right one is using run. Now when a program calls this start method, a new thread is created, and the code inside run method is executed, new thread, while if you call the run method directly, no new thread is created, and the code inside run will execute in the current thread. All right, so run means it will just make use of an existing thread, whereas start means it will create an entirely new thread. And that's what so here is a pictorial representation of that strategy. So what is happening with start is you are basically utilizing, so everything is basically done in one single thread, 1 2 3 4 5 6, but here it is basically making use of the same thread over this line. It is making reusing this number 4 thread over here again. It is making use of number 2 thread over here again, 3 here again. So using this run method, you are basically saying that, well, reuse most of these thread. These black color things are reused threads, and red means a new thread is being created. So if you just calculate the number, you will see that here using this run method, by reusing the thread, we are only creating 8 different new threads, these red color number, and here we are creating 15 different threads, which are this like red color number, so which is kind of double from this approach. So and also, so whenever you are reusing several of the threads, you really do not need to wait for one of the threads to complete. You can do the left dot join only, and it's done. So a huge amount of overhead is just reduced. Actually, it's just getting half if you use this divide and conquer approach, and it implements it gives you a very big performance gain when it comes to the real world. So here is an actual code using this start and join method, and here it is just like fork and then right dot compute. Instead of this run, we have used the recursive task as a function construct called compute, which basically invokes the run method inside. So you can use all these things, and then this program. So this is the real implementation. So let's see this implementation in the in a practice. So here is the Java code. So let's go to this demo.java, and here let me just run this thing. So this demo.java is going to show you the wasteful approach of thread.start. So let me just uncomment it, and let me just run this program over here. So if I just run it, it is taking some time, and All right. Okay, so it has a duplicate class sum thread because I am using the same name for both the things. So let me just comment out this demo2 program. So here it is, because demo2 and demo1 are basically the same program other than those 3 or 4 lines of code change. Instead of start, we are using the compute method basically. So here, let me just run this program once again. So here, all right, so here basically it ran. So just focus on this parallel runtime over here. So here it is like this, and then let's say it is giving me this result. And whereas the demo 2, if I just run like this, so let me just comment this demo 1 part over here. So if I just run this program, so here it is taking the parallel runtime is something like this. So over here, so as you can see, it is significantly less compared to here. So here it is. So here it is something like 64867541, but here it is 74464472. So these are all the different types of things, and this difference will keep on increasing if you just increase. So you can just try with many different numbers and let me know the results in tomorrow. So you can basically change these numbers. Let's say right now it is only using 10,000 numbers to sum. So you can just increase it to something like, let's say, 100,000, and you can easily see at that time basically this performance difference are becoming more and more and more all the time. So let me just run this code. So here, well, you can see a little bit of a variance in the performance, I mean in the time basically, but as you will see that, well, I mean it will be more or less like the similar thing. Okay, so this way you can have a significant amount of benefit over this type of over this type of by writing this type of conscious code, like instead of using start every time, you are just using run and all these things. So any question so for now? Did you all understand the difference between this start and run? All right, so if you have any question, please let me know. Otherwise, we can discuss it later. I mean, otherwise you can always get back to me in tomorrow's lecture and I can answer all these questions. So this is the Java program, and now, well, to get the good result with Java fork and join, what you have to remember, you have to take care of the sequential threshold basically very nicely. You have to try with the different numbers and you have to come up with those things. And also you need to know that library needs to warm up always. And it you may see the low results before the Java virtual machine and re-optimizes the library internals. So when you are basically running it, Java needs some warm-up time, and after that it will just start giving you the optimal result for multiple threads. So those things happen. So when evaluating speed loop computation to see long-term benefit after these optimizations have occurred. So all these things should be taken care of, should be considered when you are actually writing the multi-threaded program. Now wait until your computer has more processor. Maybe this 4 processor is not a great choice, but parallel 4 processors or some 4 cores or something like that, it's not a great choice. As I was saying, it is not capable of handling so many threads, so there may be several overhead time is significantly more. But well, whenever you move to some server computer, it will be great. I mean, you can easily start seeing the benefit. And of course, you need to be very much cautious about the memory hierarchy issues. We will not focus here for this course. So all right, so those are the different things related to fork and join program. And I have already shared the code with you. Just try to make use of the code, reuse of the code, or if you want, you can abuse the code also. You may see, so I'm also, whenever you have any type of question, if you get some issues, if the code is not working properly on your machine, or something is happening, something is not correct, if you observe some kind of bug in the program, always talk to me. Feel free to talk to me, or feel free to send me an email that, hey, this is not working, so what is the problem? I can work on it, and I can fix those bug and all these things. But you can do that at your free time after this class. So that's in our fork join type of programming. Now I am going to give you a better idea, or a beginner's idea of this map reduce type program. So any question before I switch to map reduce? Okay, Ambika has asked, will using run method always work, or will there be any shortcoming? Well, I really do not see there is a shortcoming as of now, but well, it possibly depends on project to project, and well, for example, and also it depends on the server to server. For example, most of the time, if you have larger number of elements, and if you have a fewer number of processor, if the gap is more, will be the gap between the number of the processor and your data amount, this run will work fine. Always you need to remember that order of that log n, where the n is the number of data, log n should be many more than the available processor. Make sense? Did you understand? If that's the case, the log n is greater than the number of processor, then your run method will work, possibly. And well, so that's what we have seen from our experiences. And also, like and honestly, when it comes to the big data problem, for which this multi-core computing is really important, at that time, you can rest assured that these things will work. Okay. So any other question? Lahori asked that if we want intermediate values after addition, then can we use run method if we want an intermediate values after addition? Yes, I believe you can do it. Oh, I got your question. So you are saying that since it is not waiting for the execution, we are not using the join method. That's what I believe your question. So well, so if you want to store the values, you can always use some kind of variable, and you can get back these values in another threads. But well, when we are trying to do a multi-threaded program, we are focusing on the deployment environment, where our focus is to get the end result back to get high performance. Now, if you want to get the intermediate result, you can always use some kind of variable and get back the result. You can use some other strategy. Make sense, Lahori? And well, I think so. I think Ambika has another question. Of other OOP language, why only Java is? Oh, okay. So that's a good question. So you are free to use any language of your choice. C provides a library called Silk or something like that. That also provides a similar fork join type of functionality. I have selected Java because it is easy to use, and it is very easy to use this fork and join. And of course, I mean, honestly, this C may have better performance advantage because C works at more hardware level. It has lots of construct, but Java programs are written in such a way it is very easy to understand, just like the library implementation. So you can just focus on the business logic, where we are just focusing on implementing the sum like that. But of course, every programming language has its own library. And not only that, right now actually Python is getting traction in the market. I'm happy that you have asked this question. Python is getting traction in the market. Python has its library called multiprocessor. So I'm just writing the name. There is a multiprocessor library in Python which offers all these type of functionalities to you to write multi-core program in Python. But the Python is a high-level language, so you just need to write the call, so you will not understand what is going on in the back end. So Python is very good for deployment if you are doing some real-world example, like let's say in industry or somewhere. It's a good choice, but for learning, it may not be a very good tool. So in one hand, C++ is taking you into very big detail. In other hand, other extreme, Python is just abstracting away all the details from you. So we have selected Java so that you can focus on the business logic. That's an optimal sweet point between these two extremes. So I hope that answered your question, right, Ambika? All right. Okay, great. So any other question? All right. So if you do not have any other question, let's move to MapReduce. Well, this concept of MapReduce basically have been derived from this map and reduce function. So while discussing about MapReduce, we will talk about the directed acyclic graph, that is DAG representation of fork join, and then I will introduce the concept of map and reduce from there. So here is the DAG or directed acyclic graph representation of the programming or trading model. So here basically a program execution using fork and join can be seen as a DAG. Basically, as you can see here, everything is basically the parent of the others. So nodes, all these nodes means these circles are basically representing a piece of work, and these edges are basically the sources must finish before the destination starts. So this parent should finish before its child will start. So that's the representation. That's how this DAG representation works. So basically these two are the process, or these two are the threads that has some dependency on this parent work, and if this parent work do not finish, these two things will not start. Similarly, this is another child which is depending on the finish of these two parents. All right, so that's the DAG representation. And a fork ends a node and makes two outgoing edges. So this is basically the representing fork. We are using fork all the time, right, to create the threads in our Java program. So this is our abstract view of Java program, like this. So, and basically these things mean, so from one process we are creating new threads, calling, forking two different threads, and then continuation of the current threads, and then join means end a node and makes a node with two incoming edges. So here it is an example of join, as you can see. So whenever you are getting these two forks, so this parent is having two outgoing edges, that means fork means creating the threads, and whenever two edges are basically joining in a node, that calls join, means end of the threads. All right, so that's how you can write the draw the visualize and draw the structure of your threading program, multi-threaded program for your multi-core computation. So it's always a better practice to visualize your workflow in the form of a DAG to do all these things. So these fork and joins are very flexible, but divide and conquer, that has a specific way of fork and join. Basically what we have seen earlier, it is basically a specific way to do these things. And honestly, many of the programs can take this type of forms. I mean, it's not only the sum, possibly sum is the beginner's example to start you working, but in the real world, lots of problems are there which can take this form, and you can get the type of benefit. So for example, like let's say there is a number of any type of word count. Many examples are there in genomic analysis workload, plenty of scientific analysis workload. They all basically works using this type of divide and conquer type of threading problems.
Yeah, so here I would like to mention the same way the FFT, the fast Fourier transform, to be computed for DSP.
Yep, exactly. Yes. So that's possibly one of the better electronic example. Yep, exactly. Thanks, Dr. Gajar. So, all right. So here there are several example, some more interesting DAG type of example, like let's say, so of course the DAGs are not always very simple, and neither all are related to the parallel problem sometimes. For example, suppose combining two results might be very expensive enough that we want to parallelize each one. So those are more involved example of multi-core computation, and many of these things are still part of active research, how to implement all these things. Vendors are coming up with different processor related things which are taking care of many different all these subtle issues and offering more and more performance benefit to the developer community. So it can take many different forms. It can take very complicated forms, and this is the responsibility of both hardware vendors and the software developer working together to provide the provide the better solution. So instead of seeing it just as a hardware and hardware threading problem, see it as a combination of problems. So multi-core computing is always like that. See it as a combination of hardware as well as software to produce a better solution, or to provide better solution. So here comes one of the thing called MapReduce, so which is basically a programming construct, and this type of dividing the things together and then joining the things together, these are so common, and so many problems can be handled by this. I mean, there is a community actually gave it a specific name called let's say MapReduce. All right, so what happened here, a map basically operates on each element of a collection of elements independently to create a new collection of the same size, and there is no combination of the result. So you can think of, like, let's say you have a very big chunk of data. You are basically chopping it off into different portions, just like what you did for sum, like taking different portion of the array. Then those parts are going for different threads or different processes, and then you are basically reduce. So you just got all the results from all the different chunks, and then there is a reduce, basically produce a single answer from the collection via an associative operator. For example, it can be another aggregation of sum, or it can give you the maximum result. So all these different things are coming under this map and reduce principle. So this is called map reduce. So basically this map reduce is so common that it became, honestly, it became the de facto standard for parallel programming. And right now, I mean, or you can say like de facto standard for big data analytics. So maps and reductions are basically the workhorses for parallel programming as of now. By far the two most important and common patterns in the parallel programming domain, which are making use of these fork and join, divide and conquer model, and made it and became the de facto standard. And we often use these maps and reductions to describe the parallel problem. For example, we will aim to learn, recognize them when an algorithm can be written in terms of maps and reduce. So there is actually a active researches are going on, and several solutions are also there. When all the problems, just to fit this model, fit this multi-threading model and multi-processor parallel programming model, many programs are, many algorithms are being proposed to take the advantage of this map reduce model, because this is a very efficient threading model. As I have shown you, that you can do some optimization of threading, you can make better use of threading, lots of different things you can do. So it's a very common practice to take an algorithm and convert it to map reduce type of things. So for example, like a word count, it's a great example of like map reduce. What you can do, either you can do the entire count, all the word, analyze the big chunk of data sequentially and do the word count. Otherwise, just take the small chunk of data, do the word count in that part. Take another chunk of data, do the word counting in that part. Do another part of data, do the word counting in that part. After that, aggregate all the results together to get all the word count. So that's what map reduce is. Map, so basically in the summary, what I can say, map means you are chopping off the data set into small chunk of data and adding and executing some user defined function. It can be sum, it can be word count, and get some intermediate result from all these small subset of the data. All these subsets are disjoint, all the computations are totally independent of others, so there is no dependency. So, and you got the intermediate result from map on each of these data set. After that, after you got this intermediate set of result, aggregate all these results together using another user defined function, which is called reduce. So that's what the map reduce is. Now it is so common, and since it became the de facto standard of parallel program, Google actually published the paper called map reduce, which has like which became the de facto standard for parallel programming. Programming for all the all the groups. It got a huge amount of traction in the community. There was an open source version called Hadoop. Possibly you have heard about this tool. There is another tool called Spark. All these framework basically offer map reduce type of programming model. It's so common. And then it basically And honestly, this map and reduce model is so nice. This type of thread and join model, fork and join model that we have discussed, it is so nice that you really do not need to limit yourself in one single machine. Let's say you have like 5 different machines and you have a big problem that you cannot handle it using one machine. Maybe your memory size is just 8 gigabytes, but the total data set that you have, it's like, let's say 24 gigabytes or something like that. So you just want to add up 3 different models, 3 different machines together. So after making a distributed computing cluster, you can easily use the same map reduce model to distribute your computation over many different machines. So at that time, of course, so this distribution takes a little bit of more things, because there is another networking coming into picture, because you have to synchronize all the systems now instead of just memory and all these things. But well, there are frameworks like Hadoop and all these things, where you can just, using this framework, you can just focus on those your business logic, and all these distribution part, like distributing over multiple machines, will be taken care of by the framework itself. Okay, so like that. And if you want to get some experience with MapReduce, you can always go to this institute website, and there is a tools page from where you can download our virtual machine, where we already have the Hadoop installed in it, and also we have several example program in here. I can share you the link in the chat window over here. So that's one of the thing that you can start looking at, and you can just install the virtual machine in your machine, and you can start writing the Hadoop program. There are demo programs and everything. And also, if you want to know more about our big data programming and MapReduce, let me see. Okay, so I think I gave a wrong name. So let me just go to this student. So if you want to know more about the big data programming, you can always go to this coding section over here, and you can go to our big data 101 course, where I am teaching like all these things related to MapReduce. All right, so these things you can do, but I strongly recommend that you download the virtual machine and start working in there, where you can just write all the MapReduce related code. All the frameworks and everything, Hadoop and whatever you can think of, are already pre-installed, and there you can start working directly. Just focus on your program. All right, so so that's about the MapReduce thing. Basically, this is a old fork join type of things, but in a different name, like these map and reduce. And with the Google's intervention in the market, it became very, very, very popular. It's a very easy to use programming model, and you can just there are lots of, I mean, all the libraries are available, so you just need to focus on the distributed computing. So anyway, so these are some of the details of the MapReduce. So what you can what you can go through the slide. I will share the slides. I am not spending too much time for discussing what is balanced tree and something like that, but you can just go over the slide. And I think these slides, if you know the concept of a little bit of AVL tree or something, you can easily understand. So but anyway, I am just since this is mostly the audience is from electronics, and I am not going into the detail of these data structure type of things, but anyway, so here it is. So that's about MapReduce. So any question before going to the analysis of parallel algorithms? Any questions? All right. So if you do not have any question, now let us focus on the analysis of parallel programming. And first of all, just pardon my spelling mistake over in analysis. Anyway, so here what we will discuss about. Uh, Sorry. So here what we will do, we will discuss about the work and span, then we will discuss about the asymptotic bound, and then we will discuss about the responsibility of multi-core programmers. So here basically analyzing the algorithms like so analysis of the algorithm means it's like all the algorithms and parallel algorithms should be first, of course, the high level. So we will start analyzing from a very high level and we'll go a little bit deeper, okay, but not so deep so that you cannot understand. Of course, I mean, we are trying to keep everything accessible at an accessible level, so anyway, so here correct, and it should be first correct and efficient. For our algorithms so far, their correctness is obvious, so we will focus mostly on efficiency part. And whenever it comes to the efficiency part, it's like the asymptotic bounds for different algorithms. Asymptotic bounds means we are trying to create some kind of function which which is depicting actually the time of computation in terms of number of data elements. So we will just try to express the time as a function of number of data elements. Well, there are of course some more details about the asymptotic bounds, which are the topic of data structure. And for this course, it is enough to know that, well, we will just try to come up with some kind of function of time. We will try to express the time taken as a function of the total number of data elements. That's called asymptotic bound. And we will design the function in such a way so that it represents like the upper bound of the time. Okay, because let's say there is n number of elements, we will express the function in such a way or the time in such a way so that as a function of the n elements, that the time will never exceed that function. All right, so that's what an asymptotic bound is. So we will just try to find an upper bound of time taken by the parallel program. All right, so that's what we are trying to do in summary. Now, let's say we want to analyze the algorithm without regard of their specific number of processors. That's the reason. I mean, we will just parameterize the processor, and then the key or the magic of the fork join framework is getting the expected runtime performance asymptotically optimal. Asymptotically again means it's the upper bound type of things. So whatever it is, upper bound will not exceed this type of things. So another assumption of this asymptotic analysis is we will simply ignore all the other hardware issues. Let's say we will ignore the processor may go wrong. Like let's say the process, there is a fault is unavoidable. We will assume that there is no fault in the system. There is no faults. There is no core segmented core fault or something like that. There is no memory issue. Everything is ideal. Just we will focus on the total number of processor and we will try to express the time of using that. So all these things. So here when so I am not sure why it is coming something like this. Anyway, I believe this is because of my changing into my Mac and Windows. Anyway, so here basically analyzing the parallel algorithms requires some, so where let's say we parameter, so work and span. So work is basically expressed as T1, which means how long using only one processor. So let's say you have one problem, you have a big problem. T1 means it is just one processor is working, excuse me, one processor is working, and how long the entire problem takes for its solution. So that's one thing. Next is the span, where the span is basically an infinity. So this is just the opposite of one. Here it is one processor, and the span means their assumption is there are infinite amount of processor. So how long it will take with infinite number of processor. So here, of course, there are longest dependence chain is there. The example is order of log n for summing an array, and something like that. And the also notice that the having like greater than this n divided by 2 processor is no additional help, because n divided by 2 is basically coming in the linear level. So, or other way, like divide the problem to more than 2n parts to take the advantage. So like this way. So these are the different types of things that you need to remember. And then also we will have like a critical path length, or the computational path depth. Computational depth is there. So this span is called critical path length or computational depth also. Like if there are infinite amount of processor, like all the things are all the things are taken care of by the processors as well. So what will be the actual depth of the divide and conquer tree? So those things are called span. So now let's connect this idea of work and span with our performance related things. Like let's say, so here is TP. So T1 was one processor, T infinity was infinite amount of processor. Here TP is somewhere in between, the real case, runtime if there are P processors available. Now we can also think of this in terms of the program's DAG. And so what is happening here, work equals T1 and sum of the runtime of all nodes in the DAG. Let's say this is the actual amount of work, and span is this infinity runtime of the most expensive path in the DAG. So all these things. So now if it is T1, then we will see that costs are on the nodes and not the edges, because there is only one node and there is not many processors involved in there. And then the lonely processor does everything. So you can easily imagine, right? There is only one node and everything is being done there. So any topological sort is a legal execution, or you can think of our some example where all the things are being done basically using one processor. So order of n is the simple maps and reduction time. So whatever be it, it will just take n times. Then there is a span, which is basically, as I have told, like the depth of the divide and conquer tree, where it takes like order of log n times for simple maps and reductions. And I have already shown that how the depth of the entire tree is order of log n earlier when we were discussing about this divide and conquer. So now here are some more terminologies. Let's say here is a speed up. Speed up means if you have p numbers of processor, then T1 divided by TP is giving you the speed up, like time to finish the work using one processor divided by time to finish the work by p processor, like that. Then the perfect linear speed up is this. If the speed up is p as we vary, and then so this is perfect linear speed up, means it's just like if you are increasing the processor by p times, you will get p speed up. So if you just, instead of one processor, if you are just using two processor, you will get 2 times benefit. 3 processor means 3 times benefits. 4 processor means 4 times benefit, something like that. So that's perfect linear speed up. However, it does not happen in real practice because of all the many different issues. So it's not possible to get the perfect linear speed up. Most of the time we get a sublinear speed up or nearly linear speed up all the time. So so parallelism is the maximum possible speed up. That's our realistic assumption. So that's the assumption, like total parallelism means T1 divided by T infinity, assuming there are infinite number of processor, what the maximum speed that you can achieve. All right, so that is it. And so here are all the different terminologies. So how to calculate the optimal TP, optimal time, if we have like P number of parallel processors. So let's say we know that T1 and T infinity, but we want the TP. Let's say P equals 4, where so what we will ignore is, in order to get this TP, we will ignore the memory hierarchy issue, caching and all these things, because as I have told, when we are doing like this type of theoretical analysis or this asymptotic analysis, we are going to take care of the ideal case only. All the other hardware issues are ignored. What is the reason behind this type of analysis? Because what the motivation of asymptotic analysis is, if you use the same machine or same hardware configuration, you are always bound to get this time benefit. So that's the motivation of asymptotic analysis. So that's why we are going to ignore all the memory hierarchy issue, because in a given platform, all those things will remain constant, but we can just focus on the number of processors. That's it. So ignoring all these things, so what will happen is less than so TP cannot be less than T1 divided by P, and it cannot be less than T divided by infinity. So most of the time the asymptotical optimal execution would be order of T1 divided by T plus T infinity. So that is so adding an extra time because of this infinite time. So all the time T1's bound, I mean the total time will be bounded by this result, this upper bound, order of T1 divided by P plus T infinity. All right, so basically here the first term dominates for small number of P, and second terms dominates for large number of processors basically. So if you are working in an environment where there are like hundreds of different processors or somehow the virtual cores and all these things, these T infinity term will dominate. And if you are working on your laptop where the number of processors are really small, then the first term will basically dominate. So this is how you can get an idea of the upper bound of all these things. Now the fork join frameworks gives an expected time guarantee of asymptotically optimal. Now expected time, because it flips coin when scheduling. So as I have told, like we are assuming lots of different things, hierarchy issues, scheduling issues, how the thread creating overhead and all these different things. But well, so that's what the meaning of this O actually. Whatever it is, it will not to go over all these type of guarantees. So anyway, so that's kind of an expected asymptotic bound. I'm not really sure your understanding of data structure, because this asymptotic time complexity and all these things are part of data structure course. At least when I did my undergrad, it was like that. So just to give you the idea that optimal TP, optimal time when you have P processors, it is going to give you the upper bound of the time can be determined by T1 divided by P plus T infinity, where T1 is the time to finish the work with one processor, and T infinity is the time to finish the work if there are infinite amount of processor, and P is the time now total number of exact number of processor. So like that way. And well, Here it is. So sorry for the duplication of the slide. Anyway, here actually the algorithm. So what happens if we just consider this sum of an array example? Here T1 means order of n, because T1 means you have only one processor and you are adding n number of sums. So if there are n data elements, you have to do n sum or n computation. 1 plus 2 plus 3 plus 4 plus, so all the different computation. If there are 1,000 elements, you need to do 1,000 sum. Or if there are like 2,000 element, you have to do 2,000 sum. Or well, not 2,000, but 2,000 minus 1, let's say 1,999 type of things, sum, if there is only one processor. But whenever there are infinite number of processor, you can utilize this divide and conquer, and you can basically parallelize lots of sum. So basically what you need to do effectively, you have to do order of only log n amount of sum, you have to do it. And so at that time, the total time, if you have p number of processor, the total time will be taken as n divided by p, where n is the total number of data points, divided by p plus log of n, where n is the total number of data points and p is the processor. So that's it. And so sum is a very basic example which is taking order of n time. As I have told, n elements means n minus 1 different sum. 1,000 means 999 sums. 2,000 means 1,999 sums. But it can be something else also. Like let's say you are doing some kind of computation, some kind of sorting or something like that, which is basically taking in square number of computation instead of n. And at that time, it may be something like after you divided and conquered this entire thing, or some kind of parallelism methodology you have explored, may not be divide and conquer. So something else where if you have infinite number of processor, maximum benefit that you have got is like order of n. So you are doing lots of things in parallel, and you just reduce the time to order of n. So your if you have infinite number of processor and exploiting the full parallelism things. Now, so at that time, the TP will be bounded by n square divided by p plus n, because you all know the formula over here, that is T1 divided by P plus T infinity, which is just replaced it, n square divided by P plus n, or in case of sum, n divided by P plus log n, something like that. And of course, as we are always saying, that we are ignoring all the overhead and all the memory issues. So that's about the time complexity or the asymptotic analysis of parallelism. Now, so after this, so what is the responsibility? So there are two-folded responsibility. As the fork join framework users or the high-level developers where we are working, so what we have to do, pick a good parallel algorithm and implement it. So I have shown you different implementation of the parallel algorithm, the bad approach, the good approach using divide and conquer, wasteful approach using start mechanism, and much better approach using the fork, using the run or compute methodology. So all those things I have shown you. So you have to implement that algorithm. Its execution creates a DAG of the things to do. Visualize, you have to visualize the DAG to take the full advantage. Then you have to make all the nodes like smallish. Nodes means the work. All the work should be smaller and approximately equal amount of work, because that will guarantee the load balancing. If one of the part of the work is taking care of a very large chunk of the data, that will take more time. So you have to give fair share to each of these nodes in your DAG. And of course, you have to make sure the percentage of the actual computation per thread is more than that of the thread creation overhead. So that's very important when it comes to a real world big data or some kind of analysis. So for example, like sum, why sum is not a very good real world example? Sum is just doing one sum which is taking only nanoseconds time, whereas thread creation itself takes like millions of sums. So at least if you do not have 1,000 sums per thread, 1,000 or 10,000 or something like that, that type of sum per thread, you cannot experience the parallel computation, I mean multi-core computation gain. So at least 10,000 elements should be added per thread. Otherwise the thread creation overhead itself will dominate. So let's say it's just like the fact, let's say I am you can easily and understand it. Let's say I am trying to add two numbers, 1 plus 2. I can easily come up with 1 plus 2 equals 3. Now let's say I am trying to do it in a multi-threaded approach. So what I will do, I will ask one of the member, one of your friend in this course, one. Then I will take another student, I will give the responsibility of 2. They will come up their result, they will give it back to me, and then I will have to add, and all these things we have to do, right? So you can easily understand the thread creation overhead. So that's what you need to really take care of it. But well, when it comes to the real big data problem in your or genomic analysis or somewhere, most of the time the computation is really huge or something like that, and sometimes in Hadoop actually, so this MapReduce framework, they give you the freedom to choose your data chunk size. So sometimes what we do is, like the data chunk size itself, we make it a little bit bigger, let's say 128 megabytes of data size, data chunk, and that will be taken care of in one by one map processor. So that way you can balance between the threads, the number of threads, the number of cores available, and the total amount of work. So just you have to, one bottom line, make sure the percentage of the actual computation, instead of summation, it can be anything, per thread should be more than that thread creation overhead. Okay, so that's one thing. And as a framework writer, so that's the responsibility of the developers, high level developers. As a framework writer who came up with these Java fork join library or Python multiprocessor library and all these things, they have to do all these part, like assign the work to available processes to avoid idling, all these different things they need to take care of. Keep the constant factors low, because every asymptotic analytics comes up with a constant overhead, like all these thread creation overhead. For example, one of these thread creation overhead is one of the big thing. That's the framework writer's responsibility. If the framework writers can create the thread creation overhead really low, which is one of the constant factor, then you can get significantly, as a high level developers, you can easily get more benefit in your program, because you can easily achieve the situation where your actual computation per thread more than the thread creation overhead. So that thread creation overhead is the responsibility of this framework writer. And of course, always your ideology will be, motivation will be to give the expected time optimal guarantee using the framework, assuming the framework user did his or her job. All right, and this is how the actual optimal guarantee. All right, so that's what we have to do. So these are the responsibility of high level developers and the framework writer. So far, any question? Ambika has asked, sir, on what basis is data chopped for subcomputation? Ambika, can you just give me a little bit more context, like on what basis. Well, there can be basically many bases what I can think of. Oh, asking about MapReduce. Well, MapReduce is just the amount of data. So let's say you have like 4 different processors, all right? And you just have to take care of the data side. So first do the computation. You probably have the idea of the computation. Now try to see that how many computations will be there in the data chunk. And then what you have to do is per map task, you have to give that many work so that the thread creation overhead is significantly less than the actual number of work, actual amount of work. Do we analyze data and then distribute them for sub-computation? Of course, you need to do a little bit of more analysis on the data and what type of computation you are actually doing. First, so MapReduce means it's nothing. Map and reduce are just two construct. Inside map, your own code is running. Inside reduce, your own code is running. So come up with that small piece of code first, which is basically taking care of some small chunk of data. Analyze that code on a small data set, that how many computations are being done there. Number 2 step, that's it. And after that, see that the amount of computation being done in that one segment of data is greater than the thread creation overhead. So let's say it is taking, let's say some computation you have done, let's say on a 2 minutes, let's say you know the thread creation overhead is, let's say 100 millisecond. All right. So you have to at least check that segment of data, one segment of the data, when you write a standalone algorithm and run it on a segment of data, that will take more than 100 millisecond. Makes sense? Did you understand, Ambika? Did I explain it properly? Okay, perfect. So just one of the best strategy is, if your computation is less, increase the data chunk size per thread or per map task. All right. And if your computation is more, then you can go for smaller amount of data size, because that will take care of the things. So guarantee that thread creation overhead is less than the actual computation. That's what you have to guarantee in summary. So that is it. And since you have asked about this MapReduce specifically, now in MapReduce basically it's not only a threaded model also, you know. I mean, I should have mentioned it earlier, because as I have told, it's used as the basis of distributed computing also. So MapReduce does not only work at the thread level, it can give you the process level parallelism also. So this entire thing that we have discussed for this thread level thing, divide and conquer and all these things, let's say in each of the, instead of each of these thread, there is a processor, and then inside each of these processes there are this threading model have been implemented. So another layer of abstraction. So divide and conquer for all the processor level, and inside each of the processor, again, divide and conquer for the threading levels. So I know it's a little bit complicated to think of, but when you have multiple processors and you want to take the advantage of all the processors, and sometimes you may need to do all these type of things. You are spawning multiple process, and then you are inside each process, you are forking multiple threads. Okay. So that's what it is going. Any other question, by the way? All right, if there is no other question, I will talk a little bit about the Amdahl's law over here and how everything is connected. And as I have told, since we did not take any break or anything, I will just finish today's lecture around like 9:15 or 9:20. So, and the rest of the things we will take care of in the next lecture. So basically it is Amdahl's law is giving you the practical example. Like in practice, much of our programming typically has parts that parallelize well, and then there are some part which does not parallelize well, which are called like sequential part. I believe all of you have the idea of Amdahl's law, and also in this course I have discussed Amdahl's law in the first phase itself. So anyway, so in summary, each of the program consists of two different parts: a parallel part and a sequential part. Now the sequential part is basically a limiting factor to the speed up. So here is the Amdahl's law in detail. I believe that you already know about this law and all these things. So here is a little bit of overview. So let the work time to run on one processor, the total time, be 1 unit of time. And if S is the sequential portion of execution that cannot be parallelized, then we can define T1 as like S plus 1 divide 1 minus S equals 1. All right. So the which cannot be parallelized. And then if we get the perfect linear speed up, that is assuming there is no memory issue, no waiting for reading and writing the data from the disk like IO wait on the parallel portion, then we can define the TP as S plus 1 minus S divided by P. All right. So sequential part is not parallelizing, and 1 minus S is the parallel part divided by P. That's what we are doing. Then thus the overall speed up of preprocessor is Amdahl's P number of processor is given by T1 divided by TP equals this formula: 1 divided by S plus 1 minus S divided by P. And the parallelism with infinite number of processors is that is T1 divided by T infinity equals 1 divided by S. All right, so this is what Amdahl's law is. So, but Amdahl's law basically is a little bit pessimistic, and maybe mostly it is bad news, but well, because it basically limits the program on the basis of its sequential part. It says that you cannot implement that much of parallelism or something like that. So here it is. So suppose we have like 33% of the program is sequential, then even if you add like billions of processor, you will never get the speed up over 3 times. Even if you add 1 billion processor, you cannot get 1 billion times speed up. So that's pessimistic. But well, whether it is really a bad news or there are more opportunities for us to do a lot of different things. So suppose we have missed some of the good old days like 980 to 2005, where 25 years or so was long enough to get like 100x speed up. Now suppose in 25 years the clock speed is the same, but you get 256 processor instead of just one. For this 256 cores to gain different like 100x speed up, we need like this type of things. 100 is less than 1 divided by S plus 1 minus S divided by 203, just replacing all these things. So which means S is less than something like that. So this is like this, but well, this is 99 point. So that gives the opportunity to the algorithm developer to come up with better algorithm. Okay, so that opened up a new arena of research utilizing this map reduce or utilizing some other open MP or MPI type of framework, where the designers basically coming up with many different algorithms and many different computational things which can which can do the things in parallel. So well, although the sequential part, having a sequential part is really a bad news, you cannot have the speed up, but of course on the other side of the coin, it opened up a lots of opportunity for the scientists, for the hardware vendors, for the designers to come up with different strategies. So researchers and the software developers are writing new algorithms to take the advantage of multi-core. Then hardware designers are trying to still take care of these hardware threads and all these things to get more speed up. New processor technologies like GPU, then FPGA are being proposed to exploit the parallelism. So, well, instead of taking it as a bad news that limited by the sequential part of the program, you can think of it as an opportunity for us to come up with different algorithms, different type of hardware, different types of processor, and all the different things. So, well, let's discuss about the Amdahl's law and all these things in the next lecture tomorrow. And so that's the overview of Amdahl's law. So let's discuss about its implication tomorrow, when I will just conclude my portion, and I will give you, like, tomorrow I will give you another 10 minutes time after the end of, so I will possibly take another 30 minutes or so, 30 minutes or 40 minutes to finish up my part, and then I will give you, let's say, 10 to 15 minutes for evaluating my lecture. That's required for our internal quality assurance process of Institute, and you can just evaluate my lecture and PowerPoints and codes or whatever you want, whatever way you want. All right, so let us stop here, and let's keep this part for the next lecture. All right, so now I will take any question if you have. I still have like 3 or 4 minutes.
So, Professor Das, I have one small question. Is there any kind of guideline or good rules of coding for the load balancing, or say, do we carry out analysis for the load balancing?
Okay, so for load balancing things, I mean, normally the type of code that I do, I always use some frameworks. For example, there is a framework called Dask. Dask has a distributed scheduler which takes care of the load balancing part. Number 2, Hadoop is another framework which does the load balancing part by itself. So, and also sometimes I use the Spark. So I normally give it the responsibility to the framework as an application developer and high-level big data developer. But possibly Dr. Gokarna Sharma can give you the idea of going into the hardware level and do all these.
Yeah, Dr. Sharma, yeah, please carry on.
Load balancing, there is a way to do load balancing, although that is not coming here. There are other techniques to do load balancing. For example, the work stealing, work sharing, and then there are other ways of load balancing too. I cover in my multi-core computing course that, but it's a separate lecture.
Yes,
it goes in a little bit different direction. But that is related to this one as well. In the future, we could cover that as well. Or maybe next year, if we do this one, then we could maybe add a little bit on load balancing as well. But there are ways to do load balancing in multi-core computing because the workloads are dynamic. When the workloads are dynamic, then we cannot predict on how much work one particular task that you assign to one processor will produce, because that might happen that when you run the code, then either you are going through the branching instruction or different function that you are running, and then so you cannot predict beforehand, and then at that time you need to use some technique that go there on the fly and then try to balance the load across different processors that are running that job.
Okay, yeah, thank you so much. So with this, Professor Das, we come to the end for day 2 session, which is on the fault join, and then you explained about the divide and conquer, the analyzing the parallel algorithms, and introduction to Amdahl's law. And thank you so much. Wishing you both of you a great and good day ahead. Thanks to all the students for remaining present till late evening. Thank you so much.
Thank you. And the other thing that I would like to tell that in the next lecture, Dr. Sharma will start presenting about the project. So that will possibly more interesting as an electronic student because that will be more focused on the hardware part. So make sure you join tomorrow's lecture and learn a lot from him. Thank you.
Right. Actually, tomorrow it will take you to whatever you learned today and then yesterday in Java, in the technique to write parallel programs and everything, and then apply it to something that has practical relevance to the day-to-day life. So basically, I will provide you a project. I mean, we were not going to evaluate that project, but what we're going to do is that I will give you a context. I will give you step-by-step procedure on starting from sequential. How do you go write parallel program, make it better, optimize, and then go further into advanced level. And that way you will learn so many different things. For example, sequential cutoff, you are going to learn about that. You are going to learn about, sequential method is actually giving time less than the parallel. And then if you write smart, then you try to see the benefit that you get from parallel. So you will get to see how to get the input data, and then and then process the input data so that it will fit in. You can fit that into your program, and then you will see the output, and then you can go plug and play, and then try to see how things are working there. So we'll start that tomorrow.
Okay, thank you everybody.
Thank you. Bye.
Thank you. Take care. Bye.
Bye.